Welcome to this screencast video on the Webel Digital Twin Pattern for Systems Modeling Language. Part 1. Simulating acquisition or creation of physical assets using activities and state machines in Cameo Simulation Toolkit. This video is not a systems modeling language tutorial, although you can learn a lot from it. This video assumes you already have some familiarity with systems modeling language, and it employs some advanced modeling techniques. It will help if you have already studied this slide trail, although you should manage fine if you are fluent in SysML and UML. To learn systems modeling language, please attend a Webel course or visit the Webel tutorial trails for SysML. The development of the initial SysML models featured in this presentation was sponsored by Greensoft, developers of software and systems for tracking environmentally friendly building and construction projects. The model in this presentation was in part developed through application of the Webel parsing analysis recipe for SysML to the following domain source document: ANSLIC 2019, Principles for Spatially Enabled Digital Twins of the Built and Natural Environment in Australia. Text extracts from the document are indicated in Webel snippet elements, an extension of the SysML element group. The source is indicated simply as ANSLIC 2019. These 5 text snippets are the basis of the initial SysML block model and 2 cases we'll be exploring: the acquisition of a pre-existing physical asset and the creation of a new physical asset. Let's examine the snippets briefly. Digital twins are dynamic, data-driven, multidimensional digital replicas of a physical entity. They encompass potential or actual physical assets, processes, people, places, systems, devices, and the natural environment. In contrast to traditional digital models, digital twins can connect with the physical twin they model, changing alongside the physical system via real-time sensors and actuators. Traditionally, industry has created digital twins by retrospectively mapping, scanning, surveying, digitizing, or developing a digital copy of a real-world object. Today, this process can occur in reverse, with the digital model developed first, followed by the physical asset. These last two form the basis of the acquire and create cases or scenarios we'll be simulating. This is a simplified block definition diagram of the main blocks that are involved in the simulation. The block physical entity refers to something that can be sensed and acted upon in the real world. It has material mass and is subject to the laws of physics. A digital entity, indicated by an @ sign, is a virtual encapsulation of a physical entity. It is also known here as a digital mapper or twinning entity. It is not the digital twin. It has a parent digital twin. It may include geometry such as 3D models, spatial information, and data on materials. By definition here, in the Webel Twin Pattern, it does not include process-related aspects. They are handled elsewhere. It may be involved in a control loop managed by its parent digital twin. An actual physical asset is an asset that is also a physical entity. It may be a pre-existing asset that is acquired, or it may be created, such as built or manufactured in a factory, typically using a digital entity initially as a creation or design template. A potential physical asset is defined here to be a tracker for acquisition or creation of a actual physical asset. Note that, as defined here in the Webel Twin Pattern, a potential physical asset is digital. It is not itself physical. It may carry additional process-related data from an asset specification. These are glued together by a parent digital twin, which, once attached, manages a sensor actuator control loop, including a single physical entity and a digital entity mapper. It may also carry additional digital mappers for process-related and other aspects. However, as defined in the Webel Twin Pattern, a digital twin block always has some physical entity with mass, which is denoted here, the physical twin. In the Webel Twin Pattern, a mere virtual encapsulation or representation of some kind of real-world process, organization, or system, such as a financial system, is not necessarily a digital twin. A digital twin may leverage one or more additional digital entity mapper objects as digital variants for optimization calculations and trade-off comparison calculations, which may then be used to drive the physical entity into a desired state. We won't be looking at digital variants in detail. Note, however, that the digital variant entities are distinct from the unique digital entity that most closely maps the physical entity. We're going to look now at the case of acquisition of a pre-existing actual physical asset by a digital twin. This scenario is based on the following snippet from ANSLIC 2019. Traditionally, industry has created digital twins by retrospectively mapping, scanning, surveying, digitizing, or developing a digital copy of a real-world object. This diagram shows instances of the blocks we saw earlier as they might be at the end of the acquisition scenario. We have an actual physical asset that is in the state exists and has been connected to an actuator and a sensor. It is a special case of a physical entity. We have the potential physical asset tracker. Note again that it is digital, not physical. It is in state integrated. It has the target actual physical asset assigned, along with the digital mapper entity. This is the digital mapper entity in the state bound, and it has a physical target, which in this case is an actual physical asset. And this is the digital twin, which manages a control loop, including a physical entity, in this case the actual physical asset, and a digital entity that maps the physical entity. It's extremely important to note that the digital twin owns the control loop. The digital twin has also been connected to the actuator and sensor, which are likewise connected to the control system owned by the digital twin. The digital twin is in the state attached. Before I show you the simulation running in Cameo Simulation Toolkit, I'll show you some of these mini state machines. It will help you to understand the simulation if you understand the states. Let's start with the state machine for a physical entity. In our case, we have an actual physical asset which is an asset that is also a physical entity. It will start in the phantom state. In fact, it is pre-existing. However, it is not until the manifest operation is invoked that the digital twin pattern knows that the actual physical asset exists and has mass. It then transitions to the exists state. Next, let's consider the potential physical asset state machine. The potential physical asset is a tracker for the actual physical asset. Note that a potential physical asset is digital, not physical. The potential physical asset starts in the state potential. We're going to go the left path through it being identified and then, as it's acquired, integrated into the system. The potential physical asset will have done its job. It may, however, be kept and useful for historical purposes as a record of the acquisition of the actual physical asset that was pre-existing. Note also that the potential physical asset may carry process-related information. However, we're not going to simulate that aspect today. The digital entity, which maps the physical entity, starts in the unbound state. After the bind operation is invoked, together with the effect behavior to bind digital, it will move to the bound state. It will not yet, however, be able to fully participate in the control loop under management of the digital twin. The parent digital twin starts in the unattached state. Only once it and the sensors and any actuators and the physical entity are connected does it become attached. And then the digital entity and the physical entity enter into a control loop managed by the digital twin. You may have noticed also these additional Boolean state flags. For example, here is attached as you enter the state attached. It's purely there as a modeling device to enable one to show states in other types of diagrams. For example, in this instance diagram, we can see the state of the various instances. From the point of view of a state machine, it may seem redundant. In fact, it can represent a single source of truth burden. So it's not necessarily a recommended practice. It's used here purely for illustration purposes. This is a run-through of a case where you have an actual physical asset that is pre-existing that you wish to acquire and twin. The tracking of the acquisition is done by a potential physical asset, which, by the way, is digital, not physical. We also have the digital twin, the digital mapping entity, which will map the actual physical asset, which is a special case of physical entity. And we have a sensor and an actuator. These have to be attached before one can enter the twinning control loop. Okay, so I have demo concrete objects here. One could get fancy and use a factory or other injection technique, but for the moment I've just created the types and feed them in. This is the main action here. So we're going to identify the pre-existing physical asset, acquire it, then attach the digital twin with the sensors and actuators, so that we can then synchronize with the physical entity. The output is the digital twin itself, which manages the control loop for the synchronization, and then we perform one single update of the digital entity from the physical entity. You can run Cameo Simulation Toolkit directly from this top-level activity diagram using the context menu. A pre-existing actual physical asset, a type of physical entity, starts in the phantom state because the digital twin does not know yet whether it actually exists. A potential physical asset tracker starts in the potential state. A digital twin starts in the unattached state. A digital entity mapper starts in the unbound state. The sensor and actuator are initially unattached. Their states are not explicitly modelled here yet. So these are all then fed in to a call behaviour action for identify, acquire, attach, physical. So you'll see as the inputs come in, they're made available on the activity parameter nodes. First, a call operation action for manifest results in the actual physical asset transitioning to the state exists. Before the manifest operation trigger on the transition causes the do manifest effect activity to be invoked, it's in the phantom state. We have asserted that it exists in the real world and has mass. In this case, we know that because it's a pre-existing physical entity, an actual physical asset. So here we see a transition to the exists state. The potential physical asset tracker in state potential is then assigned to the unattached digital twin, followed by the actual physical asset. The actual physical asset is then set as the tracking target of the potential physical asset via the call operation action for identify. Here we see the do identify effect behaviour from the transition, and the potential physical asset transitions to the state identified. Now it's time to populate our digital entity with data and info about the physical entity it maps. There are lots of different kinds of data and information one might glean from the physical entity or actual physical asset, but usually they won't be in the internal format for a digital entity, and some may not even be in a digital format at all. These stub activities represent measuring, surveying, taking information about the physical entity, and then we send it to populate digital entity, where the information is extracted, and in the case of a digital entity mapping a physical entity, the information is translated to an internal format, but only information that is not process related. So there might be 3D model data, materials data, but process related information is handled separately. A call operation action for bind then assigns the physical entity to be mapped by the digital entity, which enters the bound state. Before the effect behavior is executed, it's in the unbound state. The physical entity is now known to exist, has mass, and is set as the property physical of the digital entity. So here we see the transition to the state bound. A flag is bound is set corresponding to the state bound. The digital entity is then assigned as the unique digital entity of the digital twin. A call operation action for acquire causes the potential physical asset to transition to the state integrated, after which its tracking job is done. Here we see the doAcquire effect behavior, which simply sets the property digital to be the digital mapping entity. So it is now transitioned to the state integrated. A call operation action for attach connects the digital twin and the sensor and/or actuator, so twinning synchronization can occur, and the digital twin is then in the attached state. Now, as we go through this doAttach activity, it's worth mentioning again that cases like this are much better handled with the action language for foundational UML. It's worth noting that an add structural feature value action will set both ends of an association. So now the digital twin is in the state attached. And finally, we indeed perform an initial synchronization at the top level. This is just a stub that shows at least that a timestamp is written, the time when it was synchronized. It's written on the digital entity that maps the physical entity. However, note that the control loop is managed by the parent digital twin. It then outputs the synchronized digital entity. The acquisition of the pre-existing asset is complete. The digital entity maps the physical entity, and both are within a control loop managed by the digital twin. It's time to look at the next case, creation of a new actual physical asset via a digital twin. This corresponds to the following text extract or snippet from ANSLIC 2019. Today, this process can occur in reverse, with the digital model developed first, followed by the physical asset. For the creation case, we have an additional input, represented here by asset specification. It stands for any information of any kind in any format about how to build or create a physical asset. It's not necessarily just digital. It could be even descriptions on paper. And typically, it is not in a compatible format. So the information has to be translated into the internal format for the digital twin system. Additionally, note that according to the rules of the Webel Twin Pattern, the digital entity that maps the physical entity may only contain data on 3D models, spatial aspects, and materials, but not processes. In this case, it's going to act as a template or prototype for the physical entity to be created, or in this particular case, an actual physical asset, which is a physical entity that is also considered an asset. The process-related information is carried elsewhere. That's now the job of the potential physical asset. It may contain process-related and any other auxiliary data and information required to describe the creation of the actual physical asset. For example, it could contain information about the process of manufacture of an actual physical asset. The state machines are mostly, as for the previous case, except for potential physical asset, the tracker, which will now be used to carry additional, including process-related information about how to create, build, manifest a new actual physical asset. Now this time we're going to take a different pathway through the state machine. We're going to go from potential to planned to integrated. The digital entity that will contain information about 3D aspects, spatial aspects, and material aspects is passed with the operation plan to the potential physical asset. Once the actual physical asset is manifested, created, or built, it will then be passed using the integrate operation to the potential physical asset, which then moves into the state integrated, and then its job is done. It then only serves as an historical tracking record of how the actual physical asset was created. So here's our launcher activity that creates concrete demo instances. It creates first the asset specification, then a digital twin, which is initially in the state unattached. It creates a potential physical asset tracker, which starts in the state potential. It creates a digital entity mapper that starts in the state unbound. And the actual physical asset starts in the state phantom. It is yet to be created in the real world. The sensor and actuator are initially unattached. Their states are not explicitly modelled here. These inputs are then fed into the call behaviour action for create physical entity from digital entity. Here we see the inputs coming in on the activity parameter nodes. The unbound digital entity is assigned as the unique digital entity of the digital twin. It is then populated with design or template or prototype data such as 3D model data, spatial information and materials data via populate digital with design models. This is currently just a stub activity. In reality, non-process related data and information would be extracted and written to the digital entity in a standard format. The digital entity template is then assigned via a call operation action for plan to the potential physical asset, which transitions from state potential to the state planned. The doPlan effect activity currently just sets the property digital on the potential physical asset. And here we see the state of the potential physical asset transition from potential to planned. The potential physical asset is assigned to the digital twin. It is then populated with any process-related or auxiliary information required to track and create the actual physical asset. This activity is also just a stub. Process-related and additional specification data and information would be extracted and written to the digital potential physical asset as creation tracker in a standard format. The actual physical asset is then created, built, or manufactured via actualize physical asset, after which it will be in the state exists. This activity is actually just a wrapper for managing the binding of the digital entity to the created actual physical asset or physical entity. The actual creation or building of the actual physical asset is represented by the activity manifest actual asset from potential asset. In practice, information from the potential physical asset and the template digital entity it carries would be used to build or otherwise make the actual physical asset as a physical entity in the real world, represented by the innermost stub make physical asset. Details of how the input information is used to create the actual asset are omitted here, but it could, for example, be manufactured in a factory. The call operation for manifest asserts that the actual physical asset indeed now exists. Before the transition triggered by the manifest operation, it's in the state phantom. The doManifest effect behavior, in fact, is just a pass-through. And then it transitions to the state exists. A call operation action for bind sends the newly created actual physical asset to the digital entity, which transitions from state unbound to state bound. The doBind digital effect activity just assigns the physical entity to the digital entity. And the digital entity transitions to the state bound. After this, the role of the digital entity as template ends, and it can take on a new role as part of the synchronization loop. The actual physical asset is then set via a call operation action for integrate as the target of the potential physical asset, which transitions from state potential to state integrated. Here, the potential physical asset is still in the state planned. The effect behavior doIntegrate on the transition for operation plan assigns the actual physical asset to the potential physical asset. Then the potential physical asset transitions to state integrated. The actual physical asset is then assigned to the digital twin, and via a call operation for attach, the digital twin and the sensor and actuator are attached. The digital twin is unattached before attach is called. We saw the effect activity doAttach previously, so we'll move through that quickly. And then the digital twin moves to state attached. The control loop cycle can then start. Here, a single update of the digital entity from the new physical entity is performed. And as before, all this currently does is write a timestamp. Note, however, that the input is the digital twin because it is the manager of the control loop. And that brings us to the end of the simulation.